In the previous chapters, we discussed about hypothesis testing about single mean or one sample mean and one sample proportion. So what we would do is we would say H sub naught is given by P equals to some P naught, some value. So this is some specified value. Or if it is about mean, we would say, sorry, mu is some given mu value. Okay, and this is a given number. So we are trying to see if the group mean is equals to this number or not, or the group proportion is equals to this number or not. So both of them, they are about one sample. Just you have one population, I mean. You have one group, and then you are testing if the parameter is equals to that given number or not. But here we have two groups. We have two groups, and then we will see if those two groups have difference in terms of their proportion or in terms of their mean. So to do so, we have two ways of statistical inference. The first one, as we did with the one sample, is the confidence interval. And the second one is the hypothesis testing. Now let's start with the confidence interval. So remember, when we do the inference, the first thing that we need to know is what is the distribution, the sampling distribution. Unless we know the sampling distribution, we cannot do any of this statistical techniques, the confidence interval or the hypothesis testing. So always we start with the model, with the assumption and the model, of course. So those are, before we go to the calculation, we have to know the distribution. We have to know whether the assumptions are met or not. So for this one particular, for this proportion, as always, we want to check, or we need to check the independence. Okay, let me write the. So assumptions, one is independence. Independent. Okay. So the first one is independence within groups. So what do I mean by this? This is because now we are considering two different groups. So each group, or the elements of each group, they have to be independent from each other. Okay, so this is within each group, in both cases, in both groups. The second one, of course, is randomization. Again, both the groups or the elements or the members, they have to be randomly selected. And the third one is group independence, or independent groups. So this means, this is important, particularly when we come to the means. And the reason is because we need to differentiate between independent groups and dependent groups. So here we have two groups or two populations, and we are selecting a sample from each one. Okay, this is sample one, this is sample two. This is population one, this is population two. Okay, P not proportion, population. So we are trying to compare these two groups, the populations. And to do so, I have to select a small sample from each of them. And based on this sample, I will compare the two groups. So the assumption that we have is the first one, when you come to this sample, each element, we want it to be independent. We want this one to be selected randomly. And then the last assumption is the two groups. These two groups, they have to be independent of each other. Otherwise, I cannot use this method or this technique. Now, suppose we have this. Suppose the assumptions are met. Now, the next is, what is the distribution of, or the sampling distribution of the difference? So when the assumptions are met, sampling distribution of p hat 1 minus p hat 2. Okay, let me put because I need to write down what p hat 1 is. P hat 1 is sample proportion of sample 1 or group 1, doesn't matter. Let's say group 1. Group 1. And p hat 2 is sample proportion of group 2. So when the assumptions are met, why do I write it again? When these are met, the sampling distribution of p hat 1 minus p hat 2 is normal model. Okay, as usual, we have the normal model. So this is important. Now, when we have the normal model, of course, we need to know the sample variance, or the variance of this model, as well as the mean. Okay, so when we come to the one sample proportion, the mean is p, and the sample variance is pq over n. So here, mean of p hat 1 minus p hat 2 is given by just p1 minus p2, the difference between the population proportions. And the variance, sampling variance, or the variance, or let's say the standard deviation of p hat 1 minus p hat 2 is given by the square root of p1 q1 over n, all inside the square root, plus p2 q2 over, well, this has to be n1 and this has to be n2. Okay, so this 1 1, or the subscript 1, indicates those are from the for group 1, and these are for group 2. So from each group we have p1, we have q1, we have n1 from this group, we have p2, we have q2, and we have n2 from this group. Those are the values that we need in order to create or construct a confidence interval for the difference between the proportion of the first group and the proportion of the second group. Now, when I say P1 and P2, it doesn't matter. You can call this one P1 and this one, this group 1, this group 2, and this group 1, the other group 2. It doesn't matter. But you may get a little bit different result, and that difference will be the sign. Because if the second value is bigger than the first value, of course, you will get a negative number. But if this one is bigger than the other one, you will get a positive value. So your confidence interval will either be on the negative side or on the positive side, or it will include the zero value, which means the lower limit will be negative and the upper limit will be positive. So to avoid this kind of confusion, always try to use the bigger one, or try to set the bigger one as the first group, so that this difference will be positive for you. And that way it will be much more easier to interpret it. Otherwise, there is no difference. Okay. So how about if we don't know the population parameters? If we don't know these values, then we calculate the standard error of P1 hat minus P2 hat. And this is given by just the same formula. Now we replace the P's by P hat. Sorry, P1, Q1 hat, N1 plus P2 hat, Q2 hat over N2. So this is the same stuff, just like what we did with one sample. The only thing is now we add another value. You remember, this is, if you ignore this part, that will be the standard error of just P hat 1. And if you ignore the first term, this will be the standard deviation of P hat 2. And now, since we are finding the difference between two proportions, the standard deviation becomes the sum of, well, not the standard deviation, the variance of this becomes the sum of the variance of the individual ones. Those are the variance, the inside ones. Those are the variance of P hat 1 and P hat 2. So the variance becomes more. So this is basically, well, if you add these two groups, let's say this group has variability of its own and this group has variability of its own, then when you combine those, the variance will kind of double. Well, not double, but it will be the sum of those two variances. That's what we are trying to say here. Okay, so we have the standard error. And of course, we use the standard error to construct a confidence interval. Now, what will be the confidence interval for this difference? Okay, because we are trying to see by how much does this first proportion, or P1, is bigger than P2 on average, or with certain confidence. Okay, we are trying to look at the difference. So we call this one two proportion Z interval. This is just terminology, it doesn't matter. Just to differentiate from the first one sample Z test or Z interval, we use this terminology. Otherwise, So here our statistic is p hat 1 minus p hat 2. This is our statistic, and this is what we are, this is our center now. Then plus or minus, now we have, as always, we have the critical value, z asterisk, because the distribution is normal, so we use z. And then the standard error, which is given by this value of p hat 1 minus p hat 2. So this is the confidence interval for this proportion. And remember, this is the same with writing p hat 1 minus p hat 2, so minus z asterisk standard error of p hat 1 minus p hat 2, comma, then we have p hat 1 minus p hat 2, now plus z asterisk standard error of p hat 1 minus p hat 2. Okay, so always remember to write the lower or the smaller number on the left side, because this is lower limit and this is upper limit. Because logically we are saying from this one to this one, from the lower one to the upper, we are going upwards. We don't write the smaller, the bigger number on the left side and the smaller number on the right side. Okay, now let's look at this example now. We have the formula, and we have here we have an example. So I didn't put the whole example because I thought this would be, I mean, we can understand just from this. So here we have 57% of 248 boys. This is about whether you have online profile or not. So 57% from the survey, 57% of the boys out of the total number of boys is this, they had online profiles, and 70% of the girls, and the total number of girls is 256, they had online profiles. So what we have here, we have N1, or instead of N1, I can say, just to make it easier or to follow the calculations, I would say NB, which represents number of boys. So this is just notation. Remember, you don't have to use N1, N2. You can use any subscript here. You can use the first letter of the name. It doesn't matter. Just try to differentiate this N from the other N. So instead of N1, N2, I would use NB, NF, NG, or whatever. So NB equals to 248, and P1, PB, this has to be P hat, is 0.57, and number of girls is 256, and P hat girls is 0.7. And then the Q becomes just 1 minus P, so this will be 0.43, and this Q is 0.3. So now we have all the values, and we're asked to find, we're asked to find the confidence interval, or to construct a confidence interval about the difference between those two. So when we say the difference, we're trying to see how this difference looks like. Again, I will, instead of P, we will do the proportion of girls minus proportion of boys, because that of girls is higher. As I said earlier, it's easier for you to interpret, to do the interpretation. Otherwise, it's okay. So we are trying to estimate this, the difference between the proportion of girls and proportion of boys. So remember, as you can see here, there is a big difference, of course, between 0.7 and 0.57, or 57% and 70%. There is a big difference. But the question is, this difference could be because of the randomness, because our samples, both of them, they were selected randomly. Remember, we select this randomly. We are not including the whole population, right? So because of that randomness, always we expect some difference. How about if I select a different sample? Let's say if I had a different sample, would it be the same difference? Do you think we will have the same difference? Maybe not, maybe yes, we don't know. What we have right now is just this evidence or this data, and we have to decide based on this data. Okay, so the question is, where would this lie, or what would be the lower limit and the upper limit in order for us to be 95% confident? What would be the interval that contains this difference? Okay, that's what we are trying to do. Therefore, using the formula, okay, so p hat 1 minus p hat 2, well, still I'm using the numbers, is 0.7 minus 0.57, and this is 0.13, I guess, yeah. And then the standard error of p hat 1 minus p hat 2 is given by, wow, over ng plus p hat b qb over mb. And if you plug in the numbers, you will get, do I have the number? I don't think so. Okay. So I have 0.7, 0.3 over 256, and plus 0.57, 0.43 over 248. Okay, so you do this calculation. I'm not gonna do this one because I didn't write actually the result. I didn't do it earlier. I don't know, but I have the limit, so I will just put that one, and hopefully you will be able to easily find the, using the calculator, you can easily find the value. So anyway, and the next one that we need to find is the critical value. The critical value, the meaning, it doesn't change. Still, we have the same critical value, is the same always. So since we don't have the confidence level, as usual, if we don't have the confidence level, we will use the 95%. So our confidence level is 95%. We want to be 95% confident. Therefore, by now, probably you remember the value. This is 1.96. Okay, for 95%, this is 1.96. Now, the margin of error, well, the margin of error, of course, is the second term. This is what we call the margin of error. So maybe if you wanted to put it in short, you can just put this one, margin of error, instead of just writing the whole expression. So the next is what is p hat 1, p hat g minus p hat b plus or minus z asterisk times the standard error of p hat g minus p hat b.
I have a question.
Uh-huh.
Are we always use the confidential level 95% or we can use other?
If not given.
Okay.
If this is not provided, always use 95%. Okay.
Thank you.
And the same with alpha. You remember alpha, the significance level, it is the same. Again, even for alpha, well, we don't use alpha here. Just I want you to remember, because if the confidence level is not given, we use 95. If alpha is not given, again, we use 0.05, which is 1 minus this value. So by default, those are the common values, or the common numbers that we use. Okay, just as a reminder, if again alpha is not use alpha equals 0.05. Okay, this is aside. I mean, this is used in hypothesis test, of course, but just for you to remember, because we were talking about this one. Yeah. Okay, so if you calculate this number, you will get, I have the values. So you will get 4.7% or 0.047, 21.3. Okay, so after doing the calculation, you will get this number. So this is the confidence interval of the difference. Now, what do we mean by this? What does this shows us, or how do we interpret this one? Well, the interpretation is the same. Here we are trying to see if there is difference between these two. Now, what do you think? Well, we haven't reached to the hypothesis test, but we can answer now the question. If these two proportions, there is a difference that we see here, like visually we can see difference between 0.7 and 0.57. If I ask you which one is bigger, of course you can tell me 0.7 is bigger than 0.57. But the question is this difference that we see here, is it significant? Is it statistically significant? That's the question that we need to answer here. Okay, we are trying to answer the significance of the difference, because by random there could be a difference. So this difference that we see could be random because of randomness, or it could be significant, statistically significant. There is really difference between the two groups. Therefore, if the two groups, the first group and the second group, if they don't have difference, what do we expect between P1 minus P2, or between the group proportion, the difference between the proportions of the groups? We expect this one. If suppose they are exactly the same, we would expect this one, right? If they are equal, then we would expect the difference to be 0. Now, we haven't reached to the hypothesis test. We will go to the hypothesis. We will see this one specifically in hypothesis testing. But even from the confidence interval, we can answer this question. Now, based on this, based on what I have, can I say those two groups have the same proportion? Or can I say the difference that we see is not significant? It's just because of randomness? Well, not really. And the reason is, when you try to answer that question just by using a confidence interval, what you need to do is you look at your confidence interval and see if the 0 number is included in here or not. okay? Because if they were equal, we would expect the 0 to be included in here. The 0 by 0, I mean this 0, because their difference has to be 0 if they are equal. But here, both the numbers, they are bigger than 0, as you can see. Okay, the difference, the lower limit and the upper limit. So what I'm saying is the P1 or P sub G minus P sub B, their difference is between these two numbers. Let me write this conclusion. So we can say we are 95% confident, the same interpretation, that the proportion of girls who post online is between 4.7% and the upper limit, which is 21.3%, higher than for boys. So this is why I earlier said you better subtract the smaller from the upper. Okay, but if you subtract the upper from the lower, remember those two numbers, they would have been negative, both of them. Okay, we would get a negative number. So here, instead of saying higher, we would say that of boys is between this and this percent lower than that of girls. So the interpretation will be a little bit different, and the negative would somehow be confusing. Usually it's more easier to use the positive number. So that's why it's better to start to subtract the smaller from the bigger number. Yeah. So this is the interpretation. And here what we are saying is we would conclude now there is difference between the two proportions. Okay, this difference that we see here is not just random. There is really, based on our data, there is really difference between the percentage of boys who have online profiles and the percentage of girls who have online profiles. There is a significant difference between those two. But if the 0 number is included, then we wouldn't say that. Okay, do we have any question? If you have any question, you can write down on the chat. Well, I may not follow it because I'm just looking at this page, but yeah, you can write on the chat if you want, or you can just unmute yourself and you can stop me at any time. Okay, so how about using hypothesis tests? The same procedure as we were doing before, but in this case now, we give this name to the test just to differentiate it from the first one. Of course, again, we will use the z-test, but now in this case, the z-test will be used to check the significance of the difference between two proportions. Now again, we check the assumptions. Well, the assumptions are the same. Okay. When I say the same, it's just the same with this one, with the confidence interval that we have seen earlier. So we consider the same assumptions, and the hypothesis test, we write it as P1 minus P2 equals to 0. So here we are saying there is no difference. Okay, this is what we are trying to say here. There is no difference. And the alternative hypothesis, we have the 3 different options. We can have the two-sided, upper-sided, or lower-sided. These are the possible alternative hypotheses. And when the assumptions are met, and H sub naught is true, then we have the sampling distribution. Minus 0. Well, you don't have to write this one actually, but over the standard error of p hat 1 minus p hat 2 follows normal model. Okay, again, we have the model that we love most, which is the normal model. So under the conditions, when the conditions are met, we have this distribution now. So using this statistic, now we can find the p-value. We know from this on, we know the finding the p-value is just the same. There is no difference. Now the only difference here is, instead of using only one p-hat, now we have difference of 2 p-hats. So this is the statistic that we are using now. For one sample, our statistic will be just p-hat. So we would say p-hat minus p-naught. And the reason why we say p-naught or p sub naught here is because our null hypothesis would have just p equals to p sub naught. There is a value here, some p sub naught. And that's what we are subtracting from our sample here, from our sample proportion. But here, this is my estimator. The difference is my estimator. And my population proportions, the difference between my population proportions, I am saying they are 0 here. You know, in my null hypothesis, look at this one. Instead of p sub naught, now I have 0. So I use this 0. Of course, it doesn't have any meaning. Just I wrote it for you to see it. Otherwise, you don't have to put it here. You can just p sub 1 minus p hat sub 2 over the standard error. That's it. Okay, you don't have to subtract it. 0 from the number. Now we use technology or z-table to find p-value. Okay, and we use the p-value to decide whether to reject or accept the null hypothesis. Okay, so let's look at this example. So here, this is about a poll that had been conducted in 2011. And here we have group of people based on their age. So the first group is, they call it Generation Y. It's between the age of 19 to 29. And the second group is Generation X, between 30 and 45. And the question here is, or the thing that we are trying to answer here is, if you use technology right before you go to bed or not. Okay. And the idea, I think, yeah. So the research is basically to see if technology or using your phone before you go to bed affects your sleep or not. So the question is, do you use technology right before you go to bed? So here, 70% from Generation Y, from this age, 70%, which is 205 out of 293, they said yes. Okay, and from Generation X, it's only 50%. Okay, so now let's look at the numbers, how to write the numbers. So I have here X1, which means the number of people who said yes from group 1. Now this X is not the X that we were using when we find the mean or something. And N sub 1 is, let me put, this is Generation 1, Generation Y, sorry. And then I will have Generation X. So from Generation 1, we have 205 who said yes, who said, yeah, they use technology before they go to bed. And the total number is 293. And if you calculate the p-hat, you don't have, I mean, if you calculate it, you will get 70, and it's already given. So p-hat 1 is 70. And from here, x sub 2 is 235, and sub 2 is 469, and p-hat sub 2 is, basically, you divide those numbers, which is 0.5. Already it's given here. Okay, now remember the steps. When we perform a hypothesis test, the first thing that I need to do is state your hypothesis. Okay, so our hypothesis is P1 minus P2 equals to 0. And how about the alternative now? If you look at the question, is this difference of 20%? There is a difference here between 50 and 70, of course. Is this difference, is it real, or is it just because of randomness? Okay, so that's what we are trying to see now. Therefore, because of this difference that we see here, our hypothesis, alternative hypothesis, will be just two-sided. So I will put it this way. And the second step is to identify your model, and of course, assumptions. You can separate those two, but it doesn't matter. As long as you check all those stuff, it's okay. So when we come to independence, within the groups, here we have two groups. The first group of age 19 to 29, and the second group, this one. So of course, this is random. As you can see here, the selection, it was random, the survey was random. Therefore, it's okay to assume, or we can assume each element or each member from this group is randomly selected. And the same with the second group. Therefore, the first independence is okay. And of course, the randomness is okay because we have already here the word. And one thing to remember, as long as the sample is selected randomly, the independence assumption, the within independence, the first independence assumption is granted. It's okay. It's more likely for the members to be independent as long as they were selected randomly. And the second independence is between the groups, which means, can we say this group and this group are independent from each other? Of course they are, because there are two different groups or group of people. We don't have the same person, for example, from this one and who will be from the two groups, or who will be in the two groups. So the two groups, they are independent of each other. So that's what we mean the group independence. So randomness, we have both of them, and the second one is the third one, independent group. And the groups are independent. So our model here is I will write it on this. So we have z equals to p hat 1 minus p hat 2 over standard error of p hat 1 minus p hat 2. So we have this one. And what is p hat 1 minus p hat 2? I can write the statistic here. So this is 0.2 0.7 minus 0.5, and the standard error of p hat 1 minus p hat 2 is 0.7, 0.2 over, what is it, n1, 297, 293, plus 0.5 times 0.5, q hat and p hat are the same, over 469. And this number, I guess I have it, or no, yeah, I do have it. So approximately you will get 0.0354. Therefore, the z will be 0.2 over 0.0354, and if you divide this, you will get 5.62. So after finding the z value, what we need to find is the p-value in order to decide. And if you notice, our null hypothesis, our alternative hypothesis is two-sided. Therefore, the p-value will be on both sides. So if 5.62 is on this side, this is my p-value, half of my p-value, and the second one is on this side, below negative 5.62. So what I need is just find this part. Okay, just find this part. And the p-value will be 2 times probability of z greater than 5.62. And this number, of course, as you can see, z is very big, therefore the p-value will be very small. So this is smaller than 0.01. Now you may ask, why do I put here less or equal to? Why don't we find the exact value? It doesn't matter. I don't care about the p-value, what the exact value of the p-value is. What I need is it small or big? That's what we need to know. Okay, because to decide, I just need to know if p-value is bigger than alpha or smaller than alpha. That's it. So you don't need to know the exact value. Just be sure if it is smaller or bigger. Of course, if it is somewhere around your alpha level, let's say if our alpha level is 0.05, and if the p-value is somewhere around alpha level, the size, then it's always good to know the value, because you have to compare those two values. But if it is something like that, if it's very small, it doesn't matter what your alpha is. Your alpha could be 0.05, it could be 0.01, it could be 0.1, it doesn't matter. For any alpha of this size, somewhere in here, the p-value is too small compared to this type of alphas. Okay? Therefore, you don't have to worry as long as the p-value is very small. Just putting this way, let's or equal to this, some small number, that's good enough. Now, what do we say? Of course, as we can see, the p-value is very small. And if p-value is small, we reject the null hypothesis. And we say p-value is less than alpha, which is 0.05. Remember, alpha is not provided here. So since it's not provided, I can use this one. But here, even if you don't mention this number, if you don't mention this number, as you can see, this is very small. So it doesn't matter for any alpha, this is small. Therefore, you can skip this. I mean, or you don't have to mention this one for any alpha. So since p value is very small or very low, we reject the null hypothesis. You can just put it that way. Since p value is very low, this is good enough. If I say very low, it's smaller than the alphas. We reject H sub naught. Okay, and our conclusion would be so we can conclude that there is between well, what was it? Yeah, the rates of surfing between generation Y and generation X. Okay, so now based on this, we conclude there is a significant difference between these two generations. And this is the conclusion step. Step number 4. Okay, do we have any question? All right, so let's jump to confidence interval for the difference between two means. Again, the idea is again the same, because now we have been doing this more or less the same thing for a while. So most of the thing is kind of repetition. It's just the formula, some of the formulas, of course, like the standard deviation, standard error, they are changing. And of course, our hypothesis test would somehow be different. Now, what is the standard deviation of the difference? So our sample estimator here will be y bar 1 minus y bar 2. This is the estimator of mu1 minus mu2. So we are trying to create a confidence interval for this difference. So we construct the interval around this difference. Now, what is the standard deviation of this bar, this y bar 1 minus y bar 2? If you remember, for a single y, for a single mean, the standard deviation was, or the standard deviation was sigma square. Okay. The standard deviation was sigma over root n. So here I have sigma square over n1. This is the variance. If this is the standard deviation, then the variance is just you square both the numbers, so you get sigma square over n. Okay, we were not using this one, that's why we weren't using it. I mean, you may not be familiar with it, but the standard deviation is this one and the variance is this one. So this first term is variance of the first group, which is the group 1, plus the variance of the second group is sigma square. Well, they have to have this subscript here, sigma square 1, sigma square 2, because we don't know if they are the same or not. So I have to use that subscript. So this is the standard deviation of the difference. And the standard error, if we don't know the variances of y bar 1 minus y bar 2, is again the same with s1 square over n1 plus s2 square over n2. Okay. So what is the distribution of this one now? What is the sampling distribution of the difference? Okay. So here.
Can you go up a little bit, just for a sec?
Sure, yeah. Here or up?
Yes, there.
Okay. So the confidence interval for the difference will be y bar 1 minus y bar 2 plus or minus the margin of error. So what is the margin of error? Of course, the margin of error is given by, now the model is student's T model. It's not Z model. As you remember, for sample, for mean, we are using T model. For proportion, we are using Z model. You don't have to confuse those two, okay? So T And then we have the standard error of y bar 1 minus y bar 2. For T model, we need the, do not write this one. We need the degrees of freedom, okay? But the degrees of freedom for this one is not as simple as n minus 1. N minus 1 is too easy. If you have n, you just subtract that one, that's your degrees of freedom. But here we have two n's. I have n1 and I have n2. And the calculation is not easy. It's so complicated, to be honest. I mean, there is a formula, but it's complicated, and I'm not going to give you that formula now. So what you need to do here is always use technology, either your calculator or your computer. Okay, at this point for this course, use technology. Okay, use technology. You don't have to worry about that one. Okay. We have an example here. So here we have, I'm not gonna read all this stuff, but we have two groups, ordinary ball and refilling ball. And we are trying to see if there is a difference between these two. Okay, the first N1 is this, they are equal. Y bar 1 is 8.5 ounces and 14.7 is Y bar 2. And standard deviation, we have those two. So based on this data, or this summary, the standard error of Y bar 1 minus Y bar 2 is given by S sub 1, oops, over N sub 1. This has to be square. Be careful on this. Even me, I forgot it. This has to be square. Here you have just S, but here we need to square it. We need to square whatever your number here is. Okay, don't just put the number as it is in here. So here it will be 6.1 squared over N1 is 27 plus 8.4 squared over 27. And this number, do I have it? I don't know. Yeah, I don't have it. And then now let's see if, do I have it open? Let's see how to find the T. Okay, so here you have this two sample. This is what you need to know, what we will use now. And instead of one sample now, we will go to two sample now. Okay, so here I don't have the data, I have the summary. I will go with summary. And then if you look at this one, the good thing about this technology is you don't have to do all this calculation now. Of course, if there's a test or something, you have to show your steps, and it's good to write them down. But here you have everything. Just by following this one, what you need to input to this one is sample mean of the first group. This is group 1, and this is group 2. It doesn't matter which one you start with. So write the sample 1. Let's say, for example, for this case, the sample 1 is, the mean is 8.5 and 14.7. Here I have 8.5, 14.7. We have the sample size 27 and 27. And the sample standard deviation 6.1, 8.4, and here I have 8.4. Okay, here you have the hypothesis test. You can do hypothesis test and you can do the confidence interval. Now, for this example, we are trying to construct confidence interval. Okay, but still we can do the hypothesis testing as well. But now our option will be, our choice will be the confidence interval. And then you can provide the degrees of, the confidence level here. So since it's not given here, we will use the 95% by default. And if you look at this one by default, it's already there. So by default, it will be 95. But if you have a different level, you have to change this number as well. And by doing so, then we just compute this. And here you have, this is, these are your values. So the difference mu1 minus mu2 is negative now here, because I don't care now which one comes first. Of course, it's always good to do the same way or to follow the same way as well, but I didn't do it here. Okay, I didn't consider that one, but yeah, still it's good to consider that one. Now, if you look at the degrees of freedom, as you can see, it's not an integer now. We had always integer degrees of freedom, but now it's not anymore because of the calculation. Okay, and we had 27, which is 54, but as you can see, the degrees of freedom is 47. It's not for 54 minus 1, it's not minus 2, it's not minus 3, it's this number. So I always try to use this. And the limits are here. Okay, the limits are here. Negative 10.21 and 0.22 and negative 2.18. Now, what would happen if I reverse this one? What would happen if we treat the first sample as you can see, there is no difference. The only thing is the negative now. The only difference here, this was negative, now it's positive. Both of them, they were negative, now both of them, they are positive. Okay, and this is the reason why I was saying, like, it's always good to have a positive, or you subtract the smaller from the upper, because this way it's much more easier now. Okay, so what do we say now? So y bar 1 minus y bar 2 plus or minus the margin of error. If you do the calculation, you will get 2.22, 2.22, comma 10. This is 1.8. We have this interval. Therefore, we are 95% confident that the people between 2.18 and 10.22 more ounces thermostat than those eating from ordinary pot. Okay, so I think now we so we are left with hypothesis testing for difference between two independent means. So let's talk about this on Thursday. We will have another session on Thursday. If you're interested, just join that session again. So I think now it's better to stop here, and it's not a good idea to go beyond this. But if you have any question about this or before this one, you're welcome. So here, I can stop the recording, but if you have any question that you want to go to the recording, you're welcome.
So I have a question about the project. When is going to be due?
Okay, the project will be next week.
Next week?
Yeah, next week on I guess Tuesday. I guess Tuesday on next week. Yeah,
So the 5th?
the 5th. Yeah, the 5th.
Okay. And that's going to be from what we're seeing right now, or is going to be from...
Exactly from what we saw earlier, the proportion. Just this. Sorry, this
Here?
one. Yeah,
From
this one.
today then?
Exactly
Okay.
from today. Yes, it's
Okay.
just you have the numbers. Did you look at the numbers, the data?
I just see it really quick. I'm not...
Yeah. So probably even you have seen it on the internet because it's just current issue. It's about the COVID-19.
Okay.
So basically, you have groups. We have states. One is Kansas, and the other is we have other states. So just like this one, you have one group which is, let's say, Kansas, and you have the other group, and you have the values for each group. You have the number of positive cases, and you have the number of deaths, and you just use those numbers to just calculate the value. So when you do that, just follow the steps and show the steps, of course. And then just like what you did with exam 2, you upload it on Blackboard.
Okay.
Okay.
And what about the final exam? When is going to be?
The final exam, I haven't decided, but I will probably, I may give you before that date, because the day is, I think, the 12th, the 12th, yeah, 12th of May.
Okay.
So I may probably send you the exam out before that day, and then you can have more time.
Okay.
Okay.
Good.